start with an uncomfortable accounting fact. The most expensive idle time in computing today is a GPU waiting for data. Accelerators are the priciest hardware in the building. Every second one sits stalled on a read. You are paying peak compute prices for nothing. Multiply by a training cluster with tens of thousands of accelerators, and storage stops being a supporting act. Modern AI training is an I/O problem, wearing a compute costume. Yet most storage conversations end at capacity and price per terabyte. Wrong metrics. The architectures that work optimize two things. First, GPU utilization. The accelerators must never starve. Second, research velocity. A researcher anywhere should reach any dataset without waiting days for copies to crawl across regions. Hold on to those two goals. Every design decision in this session, the hierarchy, the I/O shapes, the caching, the metadata, is downstream of them. And at the end, we will see one of the largest AI fleets on earth apply every single one. The foundation concept is the storage hierarchy, and it is best drawn as a pyramid. At the top sits host memory, nanosecond fast, cruelly small, and the most expensive bytes you own. One step down, flash on the GPU host itself, microseconds away, terabytes, not gigabytes. Below that, a regional flash fabric, disaggregated solid-state storage shared across a whole region's clusters, holding petabytes at millisecond latency. And at the base, the global disk fabric, hard drives, exabytes of them, the cheapest durable byte available and the slowest. Here is the design truth. Every level trades roughly an order of magnitude of latency for an order of magnitude of capacity per dollar. No single tier can win alone. Memory cannot hold your datasets. Disk cannot feed your accelerators. The architecture is not any one layer, it is the choreography between them, which raises the real question, what should live where and when? To answer that, you need to know what training I/O actually looks like. Training does not have one I/O pattern, it has three and they want different homes. Shape 1, dataset streaming. Epoch after epoch reads the same enormous corpus, mostly sequentially. Write once, read many, the friendliest shape imaginable and the most cacheable workload in all of computing. Shape 2, shuffled sampling. Stochastic training wants randomized order, so reads scatter across the dataset. Random access is the natural predator of spinning disks. A hard drive that streams beautifully collapses under seeks. Flash shrugs. This shape alone justifies the middle of the pyramid. Shape 3, checkpoints. Every interval, thousands of workers dump model states simultaneously, a synchronized write burst. And when a job restarts, thousands of hosts demand the same checkpoint at the same instant, a read storm aimed at a single object. Three shapes, three different demands. Sequential streaming tolerates the disk fabric. Shuffled sampling demands flash. Checkpoint storms demand fan-out. Any architecture that treats these as one workload will fail at least two of them. Now the central pattern of the whole session. Because training data is write once read, many you can commit to a rule that simplifies everything. There is exactly any authoritative copy of every dataset, and it lives at the bottom of the pyramid on the cheap durable disk fabric. Every faster tier above it, regional flash, host memory, is never a home, only a cache. This single decision buys you enormous simplicity. Caches can be dropped, rebuilt, resized, or lost without ever endangering data. Placement stops being a migration problem and becomes a caching policy. Promotion is explicit. When a training job schedules, a prefetch call hydrates the regional cache ahead of the first epoch, so the job's first read is already warm. Eviction is boring on purpose. Time to live and least recently used policies. Made quota aware, so one greedy team cannot flush everyone else's working set. The source of truth stays boring. The cleverness lives in the caches. That division of labor is the architecture. Here is the failure mode that surprises teams who did everything else right. The data path is fast and the metadata path eats the win. Before a data loader reads chunk 17 of a dataset, something must answer. Where is chunk 17? At exabyte scale, with billions of objects sharded across regions, that question can bounce through multiple services. A directory here, a mapping service there, a region resolver after that. Each hop adds latency to every single batch forever. The fixes are unglamorous and decisive. Collapse the schema, store the layout so that locating any chunk is one constant time lookup, not a walk. Cached plans, the resolve map of chunk to location, right next to the compute, so the answer is a millisecond or two away instead of a cross-region question. and treat metadata capacity as a first-class scaling dimension, budgeted like bandwidth. The pyramid moves bytes. The metadata plane decides whether the pyramid gets asked efficiently. Both have to scale together. Time for the evidence. In July 2026, Meta published its AI storage blueprint, and it is our concept slides made concrete at hundreds of exabyte scale. Their hierarchy, layer by layer, L1 is GPU host memory, L2 is flash on the GPU host, L3 is a regional disaggregated flash tier, and beneath it all, a global blob storage fabric backed by hard drives, the ultimate source of truth, exactly the one boring copy pattern from slide 4. The moving parts carry names worth knowing. Tectonic, the regional multi-tenant storage fabric, provides the block layer. OWL, a distributed caching subsystem, is woven directly into the storage SDK. ZippDB holds the collapsed metadata schema, and a client called Block Client streams data straight from the fabric into training hosts. Datasets are write, once read, many. The L3 flash tier holds data for a configured period with TTL and LRU eviction, quota aware per tenant. An explicit prefetch API hydrates caches ahead of the job. Every pattern from this session shipping in one production fleet and the results in their own numbers. The distributed cache achieves an average hit rate of 80%. 4 of every 5 reads served from flash near the accelerators instead of the distant disk fabric. Metadata lookups, once multi-hop regional queries, now resolve in 1 to 2 milliseconds with a constant time lookup per chunk. The slide 5 fix deployed. Researchers reach datasets from any region through the same prefetch and cache path, which serves the second goal from slide 1, research velocity, no more waiting on cross-region copies. Just as instructive is what Meta names as unfinished supporting checkpointing without stalling GPUs at even higher scale. Remember, shape 3, the synchronized write burst and the restore storm. At the frontier, that is the IO shape still fighting back. When one of the largest fleets on Earth tells you where it still hurts, that is free strategic information. The checkpoint part is where the next generation of storage architecture will be won. Let's make the cache argument with arithmetic, because the numbers are startling. Suppose the flash tier is 10 times faster than the disk fabric. With an 80% hit rate, the average read costs 80% at 1/10 the time, plus 20% at full disk price. Work it out and effective latency drops to about 28% of disk. Only call it 3.5 times faster storage without replacing a single hard drive. Push the hit rate from 80 to 90% and you are approaching 5 times. This is why the source of truth can stay on the cheapest durable medium. Hit rate math, not hardware heroics, sets your effective speed. It also reveals the real cost of a bad eviction policy. Every percentage point of hit rate lost is a direct tax on effective throughput, which is a direct tax on GPU utilization, which is the most expensive resource you own. Cache policy is not a tuning detail. At this scale, it is a financial instrument. The portable checklist, whether you run 100 GPUs or 100,000. 1. Instrument GPU idle time attributable to data, not IOPS, not throughput. Accelerator starvation is the KPI because it is the metric denominated in money. 2. Designate one boring source of truth on the cheapest durable tier and demote every faster layer to a strict cache. If losing a tier would lose data, it was not a cache. 3. Promote explicitly. Schedulers know which datasets a job needs. Prefetch before the first epoch, don't fault your way to warmth. 4. Evict with quota-aware TTL and LRU, so tenants cannot starve each other. 5. Match tiers to IO shapes. Streaming can write disk. Shuffle sampling needs flash. Checkpoints need burst, absorbing fanout. 6. Budget metadata like bandwidth. One constant time lookup per chunk. Cached near compute. 7. Rehearse the restore storm. Thousands of hosts. One checkpoint. Same instant. If that scenario is unplanned, it is an outage on a timer. Landing it. AI training is an IO problem in a compute costume, and storage architecture answers to exactly two masters. Keep the accelerators fed and keep researchers moving. The answer is not a heroic single system. It is a pyramid with discipline. One boring, durable, cheap source of truth at the bottom. Strictly cached tiers above it, promoted by explicit prefetch, evicted by quota-aware policy. Metadata collapsed to constant time lookups cached near compute. And the whole thing justified by hit rate arithmetic. 80% hits on a 10 times faster tier is 3.5 times faster storage. Money printed by policy, not purchases. Meta's blueprint shows the pattern holding at hundreds of exabytes and honestly names the next frontier, checkpointing without stalls. That is the architecture: boring bottom, clever middle, fed GPUs. If this session sharpened how you think about the pyramid, the next lecture in this series takes the same concept, first lens to another piece of modern infrastructure. Thanks for watching.